All right, welcome everyone to the GDS webinar today. My name is Jay Ren. I'm the current chair of the topical group on data science APS, and I am joined together with a fantastic panel of presenters and chair for this webinar today, and this is part of our ongoing GDS virtual webinar series. We are in our 7th event here, and I am very, very excited to see you here. Let me switch to, okay. Thank you for registering and attending the live events. And if you happen to miss any of the prior sessions, we have recorded and posted all of our prior sessions on our YouTube channel. Please feel free to follow us on YouTube. GDS APS is our name. You will find fantastic talks and tutorials in data science application, in physics and physics education. There are many great sessions that we have posted. And in addition to YouTube, we are also on LinkedIn, on Twitter, on Facebook, Slack. We have a Slack channel, and of course, we have an email, gds@aps.org. And I hope that you can stay connected with us via your favorite means of social networking. And of course, if you have any suggestions or webinar topics, if you have great contents to share, please feel free to reach out to us. We would love to hear from you, and also would like to invite you to our GDS family. As of right now, the GDS is having open calls for March meeting 2021 session proposals, and we're also calling for nominations for APS fellows. So again, any thoughts or suggestions, please let us know. For the webinar today, our webinar is titled Molecular Dynamics Ex Machina, and it will be chaired by Professor Boris Kozinsky together with Emily. We have three great presenters lined up, and I will hand this to Boris right now. Please, I know that you will be muted during each of the talk, but if you have any questions, please feel free to use the questions box on your tool column to submit questions anytime. And at the end of each presentation, we will try to unmute you if timing allows for questions and for interactive discussions. So with that, I will turn it over to Boris.
Thank you, Gia. Very nice to have everyone join us. So this was initially intended, of course, as an invited symposium during APS. So it's very, very good that we actually are able to do this now. Again, the motivation for this session was to look at some of the emerging tools bringing machine learning to accelerate simulations, atomistic level sampling of configurations and molecular dynamics. And Em and I were thinking to bring together some of the leading players in this field to tell us a little bit about what are the challenges and what are some of the emerging solutions to efficiency questions, how these machine learning models can be transferable, accurate, and how do we build in some also physics into their presentations that these machine learning models need. Okay, so I hope today is just the first installment of the series of talks on this very important topic, molecular dynamics, ex machina, as we call it, sort of bringing machine learning and the molecular dynamics tools together. So today, the first speaker will be Milica Todorovic. She is a research fellow and a unit leader at the Department of Applied Physics in Aalto University, and she has degrees in physics and material science from University of College London and Oxford. And now she's specializing in method development for large-scale first principles calculation and their application to advanced hybrid materials. And she's focusing her research right now on interfacing artificial intelligence algorithms with first principle simulations of materials and optimizing material functionality. Okay, so welcome, Milica, and you have about 30 minutes, and then we'll have 6 minutes for questions.
Okay. Thank you very much, Boris and Amina, and thank you not just for inviting me to this very interesting focus session, but also for being so active in this digital series of seminars, which I found very useful. So greetings everybody from Finland, socially distancing Finland. My name is Milica and I come from Aalto University. So today I will tell you about how we do smart sampling for chemical property landscapes with a tool we call BUS. So this work has been developed in the group of Patrick Rinke at Aalto and in collaboration with computer science experts Jukka Korenter, who's currently at Oslo, and Michael Gutman at Edinburgh, UK. So in our group, we do ab initio calculations on functional materials, and they typically involve organic and inorganic hybrids, like what you see here. So we have large molecules like these. C60 is a typical electron donor, pentacene a typical electron acceptor, and this is all housed in some solar cell buffer complex oxide material like the titanium dioxide. And these are the systems we look at a lot, and we want to first know their structure, because structure determines their functionality in devices, and if we can possibly find out how to tune functionality, we can optimize their operation. And the first question we always ask is, what is the structure at the organic inorganic interface? Because this is a big bottleneck for device operation. Now, hybrid interface structure is really difficult problem. Even if you know everything about your organic solid and the molecules, everything about your crystal, it's really not obvious what kind of interface structure might form. Due to this complex bonding of short range and long range interactions between the organic and inorganic part, you might have different thin film morphologies. And it's not even easy to predict how a single molecule might absorb on its own. So the first thing we have to do is DFT-based structure search for molecules and surfaces. And there are lots of problems with DFT structure search. Our simulations usually involve many atoms, quite large molecules, big chunks of substrate, so they're pretty costly. I mean, we run them for days or weeks. In order to know which structures are the most relevant and stable, we need to look at many different structures, so there's a lot of structural sampling involved. So to avoid this, what people typically do is maybe use intuition to guess what structures might be viable, but this is a risky problem because you never know if there are any other structures that might be even more stable. We just didn't think to check them. So we thought it would be great to use AI to do some kind of AI structure search to solve these problems. Now, there's not much we can do about DFT. We definitely need chemical accuracy. We have to keep that. But maybe we can do some kind of smart reduced sampling to solve a sampling problem. And as for intuition, we really don't want to do that. So ideally, the machine would just look at energies and tell us what are the low energy structures. So the solution we came up with is to interface our DFT codes with some kind of AI algorithm and leave it to the machine to choose to look at relevant kind of molecule on surface configurations, learn about their energies, and then from there predict which ones are the most stable. And there is one thing that we can do. We can encode some prior knowledge about the chemistry of these systems. So we know, for example, that in an absorption scenario, the structure is unlikely to deform very much. And the same for the molecule, it's not going to disintegrate. So to first approximation, we can keep these structures fixed, and we call this the building block approximation. And now an adsorption problem just becomes a function of the translation or the position of the molecule above the surface and its orientation around the surface. So here, if you want to really look at how you look at the orientation, this is an example. So the translation is described by this XYZ translation of the center of the molecule, and the orientation as shown in this animation by rotations with respect to X, Y, and Z axes. And what this does is it takes the energy from a very large dimensional problem of every single position of every single atom in the system to a function of effectively kind of 6 variables, the position and the orientation of these molecules. And this dramatically reduces the search space that we have to handle, and effectively also allows us to not worry about the chemical search space, but only about the configurational search space. So all of these elements we included in this approach we call the Bayesian optimization structure search. Bayesian optimization is our key AI engine. It drives the code. We need some data. These come from total energy simulations, and we have this building block concept I just introduced. So I'm going to explain these a little bit more now. First, the Bayesian optimization. So if you didn't meet this term much before, this is a well-known method in computer science for complex optimization. It is very powerful at finding global minima on unknown functions very fast. And it does that by guessing a shape for that unknown function called a surrogate model, and then refines it iteratively with some data. So the way this works is you need some data to start, and then the Bayesian optimization is a two-step process. The first step is Bayesian regression, where you fit that data and you find a surrogate model, and then you evaluate an acquisition function which will tell you where to sample the next data point for maximum benefit. And I'll come back to this. So then you make the evaluation, you add it to your data pool, you perform the two steps again, and on you go until you refine the surrogate model. So let's talk a bit about Bayesian regression. What we do is we fit the surrogate model with Gaussian processes. And Gaussian process, if you're not so familiar, it is illustrated here. It's just a distribution over functions. So here on the left, you have a Gaussian process prior. If you don't know anything about the data, this is what a Gaussian prior look like. Your surrogate model could be any of these functions. They vary randomly through space. And we simply don't know which one is the solution for our problem. As soon as you acquire some data points, like these two, you can apply the Bayes theorem and go from a Gaussian process prior to a posterior. And what this step does is it effectively collapses the space of many, many possible functions to only those that pass through the data points. There are still many possible functional forms we could have, but they have to pass through the data points. So all of these dashed lines now are a possible pool of functions that remain, and you can compute their mean. This is called the posterior mean, and this is the most likely look of the surrogate model. All the space spanned by these possible functions is described by the posterior variance, and the variance is a measure of our confidence on the surrogate model. So where the model passes through the data points, we are very certain. And this is where the variance disappears. But where we don't have any data, the functions could still vary quite a bit, we just don't know, so the variance is large. Now, with these Gaussian processes, any 2 points are actually Gaussian distributions, so they have a mean and a spread, and any 2 points are connected through a kind of a covariance function where a kernel enters. I'm showing here a very commonly used kernel for us, a Gaussian or a radial basis function kernel, and it has 2 hyperparameters. This is important to note. The signal variance, which multiplies the Gaussian, describes how much the function might vary on the y scale. And the length scale describes the variation in the x scale, for example, how many minima it might have. The important thing to note is that these are fitted every time the model is fitted. And so as we refine the model, these also somehow converge, self-converge. So we don't really have to worry about setting these. They are naturally converged. After we have computed the mean and the variance for the Gaussian process given the data, we have to use an acquisition function to sample the next data point. Now, the acquisition function is supposed to tell it what gives us the maximum benefit, but that really depends on the user. You might want to find the global minimum first or find the entire function. We like to do a bit of both, so we use this exploratory lower confidence bound acquisition function, which is shown here. So it is plus the posterior mean, literally the mean line, minus square root of a factor multiplying the variance. And we're supposed to find where this function takes a minimum and then evaluate the next point there. Now, it's no accident that this function has these 2 parts. If we forget about the one on the right, and we look at where this one takes the minimum, well, it's where already we have the global minimum. So minimizing the posterior mean just means we're looking for a minimum nearby where we already have a minimum, and this is called data exploitation. And if we forget about the part on the left, we're looking to sample where the negative variance is minimal, and this is where the variance is large. And this is inevitably where we have no data, and this is why we do exploration here. So the form of this function is to basically do a little bit of both exploration and exploitation, and this is a very efficient way of finding the global minimum, as I will show in a similar example. This is a 1D example. We have on the left a function shown in blue. That's the true function. We know what it is. It's energy as a function of angle. And it's somehow complicated. It has a global minimum in the center and one local minimum here to the left. So with 3 points, we can try to sample this function, and we have these 3 red points, and we fit the the black line. That's our model. It's not very good. It thinks the global minimum is where the green line is, and the dashed lines show that the uncertainty is literally off the charts. So as we go from 3 points to 6 points, we're going to do a little bit of exploitation. So we're going to sample 2 points to the left and the right of the global minimum location. And accidentally, this gives us a very good guess of the global minimum. And now we've improved the model function greatly. And we already know where the global minimum is. We also sample one to the left, and this is because of exploration. So there's huge uncertainty there. So if you want to just find the global minimum, this is where you stop. If you want to find the entire function, you keep on sampling. So if we go from 6 points to 9 points, we will sample again a little bit close to the global minimum, and we don't actually find much new here, but we improve the curvature. And we sample again on the left-hand side, and this helps us hit the local minimum. And now we have an entire function converged in just 9 points, and we can read off the positions of the global and the local minima there and the barrier between them. So this is how Bayesian optimization works in practice. We start with some data. We do this 2-step process until our either global minimum is found or the model converges. And the Bayesian regression really is what delivers this surrogate model for the energy. We frequently look at energy so we can find stable adsorbents. And this tells us about the functional relation between structure and energy, and about the global and local minima and the barriers between them. So this was the Bayesian optimization part of BOSS. A little bit more about the other parts. I mentioned already these atomistic building blocks. So keeping groups of atoms fixed is a well-known idea in structure search. Jörg Baylor used it ages ago. Alganov now uses it in USPEF. In our case, our industrially relevant molecules frequently have big aromatic chunks that we can simply keep fixed, or functional groups that we can keep fixed. So torsional angles are good variables here. When it comes to adsorption problems, molecule surface distance orientation are good variable. The important thing is that this allows us to sample configurational space instead of chemical space. For finding stable adsorbents, we kind of need total energy. You can plug in any total energy method into BOSS. We frequently work with force fields, and for some more accurate problems like comparison experiments, we have to use DFT. So this data acquisition is expensive, and we typically use high performance computing. So like this theta machine at Argonne, which we use. The good news is that from each data point, you needn't only extract the total energy, you can also extract components to the energy, the HOMO-LUMO gap or the band gap, molecule surface charge transfer. So all of this can be extracted, and we can build simultaneous chemical property landscapes from all this information. Here's a very early example of how we did this in 4D with alanine. It's a very small molecule, but it has 13 known minima, and it has this well-known functional groups, which we can keep fixed into building blocks. And now the total energy problem for conformer search just becomes a 4-dimensional problem of 4 torsional angles. And this is how BOSS deals with it. So it does many acquisitions with these 4 torsional angles. It builds a surrogate model, and from there we extract the global minimum, which is shown on the graph below. And the structure on the right is corresponds to the graph below. And you can see that in the beginning, the global minimum guess is not very good. The energies are high, but then as we acquire more points, it's lowers and lowers, and the predicted structure changes until it basically changes no more. And this convergence is achieved at about 90 points. So we checked, and this is indeed the global minimum conformer that was identified in literature. So one thing that is of interest to us is the efficiency of finding the global minimum as a function of dimension. So this is a problem with 4 dimensions, but we could also look at the 3-dimensional, 2- and 1-dimensional components. And this is how this looks like for alanine. So on this graph, on the y-axis, you have the number of data points to find the global minimum, and on the x-axis, the dimension. So you can see with the blue and yellow curve, this is the Gaussian kernel, which is frequently used. But this kernel scales very badly with dimensions. So the number of points needed for global minimum is really high, already at 4. Now, we like to use a standard periodic kernel where you tell it that your your variable is periodic, like in the case of an angle. And this is the green line. So this is a considerable saving in the number of points. And if you give the standard periodic not just the energy point, but the gradient of that energy, you can get another 50% saving. And we tested this more on alanine dipeptide, which has up to 7 degrees of freedom. And you can really see that with gradients, you can find you can solve the global minimum in 7 dimensions with about 70 points. So this was nice for testing, but what we're really interested in is applications on organic and inorganic interfaces. So I'm going to show you 3 examples. In the first example, we had an actual experimental structure to compare to. So we used Boss-defined structures, and we tried to then verify our predictions. In the second case, we found somebody who was recording experimental landscapes, energy landscapes. So we were able to verify our energy landscapes against experiments. And in the third case, it was a study that we had done with the kind of traditional structure search interfaces. And then we plugged it into Boss, so we were able to evaluate how the AI performs against the human. So let's start with the first case. This is C60 on titanium dioxide anatase, so very classical solar cell material for us. And here on the left, you can see all the acquisition the Boss makes in these 6 dimensions. And on the right, you can see from the top down what the predicted global minimum structure looks like. And you can see it's really looking for the best orientation here. And then after some time, it will stop moving. And this is kind of the one that it's happiest with. So if we look at the global minimum evolutions in the top graph, you can see this gray line. And this is how the global minimum prediction converges as we sample more points. And it's clear that after about 350 points, things don't really change a lot. So this is not bad, I guess, for 6 dimensions. Meanwhile, all the red dots are all the acquisitions we're making. So, and the dashed line shows that the average energy of these acquisitions is way above the global minimum. But we're learning so much about the surrogate model that the global minimum prediction is improved. Now, the best thing about these n-dimensional models is that you can cut them in dimensions that are somehow chemically meaningful. So here's an XY map of the 2-dimensional slice through this 5-dimensional model in the XY plane of the substrate. And you can overlay this with the substrate atoms and clearly see that the global minimum is found near this 5-fold coordinated titanium atom, which is what is expected from the chemistry of the surface. So this is like interpretable chemical insight we get from machine learning. Now, we used this surrogate model to extract the lowest energy points, and then we relaxed all degrees of freedom. And we found that the lowest 3 structures with the lowest energy are these, 2 degenerate ones and one slightly different. Now, we also found that somebody had done experiments on this system and imaged C60 on the surface with quite a bit of insight, atomistic insight. And you can see from the top that you get these kind of oval structures with 4 different aromatic rings in the experimental images. So when we looked at our structures top down, we thought that we could in most cases identify these oval structures with 4 aromatic rings. And we tried to identify what is their orientation with respect to the substrate. But then when we went back to these images, unfortunately, we had no resolution on the substrate, so we couldn't identify the same in the experiments. But we thought that it looked pretty likely that one of these structures was actually in the experiment. This worked so well that now we continued to work on chunky molecules and surfaces to help the experimental colleagues who are trying to image this. So here's an example of camphor on copper 111, where we did exactly the same. We did a structure in 6D, and then our student Yari extracted all the minima, and he found 8 different structures come out of this landscape. And we found 2 categories. The one on the left has the oxygen always pointing down, and the one on the right has the oxygen pointing up. So when we looked at their energies, it was clear the one on the left were much lower in adsorption energies. So this is likely chemisorption, and the ones on the right were physisorped. And this was indeed obvious when we looked at their partial loss. Now, it looks increasingly likely that these chemisorped structures are behind all the different experimental images obtained for this molecule on the surface. You see that there are different kinds of molecular orientations observed. But we have one more selection criteria. In order for these things to be imaged, they have to stand still, so not diffuse and not rotate, so they have to be somehow fixed in place. So we went back to our potential energy landscape and we data mined it for all kinds of barriers. So on this graph, you see the blue barriers correspond to lateral mobility for diffusion along the surface, and the red barriers correspond to kind of in-place rotation. And it's really these four structures that look like the best candidates for really stable and static structures on the surface. And now we're in the process of identifying it. And if you want to know more about this work, you can read it in this freshly archived paper. Now, we were very excited about computing all these potential energy surfaces, and we were even more excited when we learned somebody was experimentally measuring it. So this is a collaboration with Yale University, where the group of Professor Udo Schwarz put a benzene on copper 100, and they used the AFM tip to kind of do these horizontal passes above the molecule with increasing tip distance. And this is how they extracted forces and energies acting on the tip and built up an experimental PEZ above this molecule. So you can see this kind of molecule is roughly in the center, and you have this conical shape, the blue conical shape, and the maximum of interactions about minus 0.9 eV, and the rest is kind of going up to 0 in vacuum. So we thought to maybe just plug the system into BOS, because benzene is really easy for building blocks, and see what comes out. So when we looked at the system, we first checked the rotational angles, and indeed we found that flat absorption is preferred. So then we just forgot about rotation, and we did a 3D energy landscape in X, Y, and Z. And this was particularly useful because you can cut it in different two-dimensional cross-sections that give you some chemically meaningful information about the system. So if you look at the XZ energy map, you can really identify the spot where the molecule likes to absorb. And if you look top down on the XY map, you can see global minimum is above this hollow site on the surface, and then the bridge is a saddle point, and then the atoms are maxima. Now, this system has been simulated before a few years ago, and what they did is the traditional way, where they just looked at 3 possible sites, and they relaxed all degrees of freedom. And we were very glad to see that our energy scales reproduced like spot on those results, even though we did no relaxation here. So this is just because the building block approximation is so good here. So having learned about the absorption of this system, we had to then introduce a tip, and then we fixed the molecule, and we used the tip to sample the potential energy surface above this molecule. And this allowed us to build a 3D computed potential energy surface for the system. And when we sliced it in the same dimensions as the experimental measurements, we found kind of a conical shape that looks similar. And here I compress it and I overlay it for better comparison. So it looks pretty good. Our kind of blue halo is also found at about minus 0.9 eV. And in the vacuum, we also go up to 0. So this is more than just kind of qualitatively good, it's quantitatively good. So we continued working with this group, and now we're helping them measure diffusion barriers on the surface. And in the last example, here's a coronene and copper oxide. This was a collaboration with our Spanish colleagues who sent a student over, and Diego was doing traditional simulations of coronene and copper oxide. Coronene is a very flat aromatic molecule, so pretty easy to do building blocks. And on the left here, you find the P2x1 surface reconstruction for this oxide. And it's got these typical AR added row features of alternating oxygen and copper atoms. So the way you traditionally do this is you find the smallest part of the surface that repeats itself. And this is shown in the blue rectangle, and then you find some typical symmetry points where you want to put the molecule on, and then you relax all degrees of freedom, and you found which is the preferred absorption site, and indeed it was copper. So Diego found this out in a traditional way using about maybe 400 DFT calculations. So then we thought, okay, this looks like easy for building blocks. Can we put this into BOS? And we did. We found this XY energy map, and indeed copper was the absorption site. And the best thing is that this was found in about 10 evaluations, so about 3% of the effort that Diego did. And the energies are very close, minus 2.5, and this difference is coming from the fact that coronene is slightly deforming when you relax everything. So this was a very good result. I mean, 3% is very good, but this was still a 2D simulation, and we wanted to check the full 3D case with the molecule rotating in plane. So this allowed us to build a 3D surrogate model, and then we cut it again in the XY plane, and indeed, this was the solution. Thank you, Boris. Now, this was a very simple surface. What Diego also did is considered a much more complex surface. Here's the C6x2 reconstruction, where you have this green atom coming in. It's another copper that distorts the added rows. And now you have to take a much larger chunk of the surface that repeats itself. And this was a tough problem. So Diego tried to estimate 7 different potential adsorption sites, and he relaxed the molecule above them. And this was about 1,000 DFT evaluations. And then we plugged this into BUS, and it took us a little longer to converge them, but we found these kinds of energy maps, which are incredibly complicated, but lots of different minima. And it's also showing minima in the sites where Diego didn't think to look. And this is a problem for most of our experimental collaborations. They work with lots of complex oxide surfaces where the lattice sites are not always well defined. So with human intuition, it's really easy to miss the relevant sites. It's much better to get the AI to take care of all of this for us. The last thing that I wanted to mention is that we've recently tried to use this with experimental data. We were approached by colleagues at chemical engineering at Aalto, and they were building tannic acid nanoparticles for biological applications. And they had these 2 processing conditions, the pH and the pKa of their base solution. And they wanted us to help them drive the particle shape between 1D and 3D. So what they did is they made a bunch of particles, they looked at them, they tried to extract the dimensions for these particles, and then we tried to, we constructed an objective function for what makes a 3D shape. So maybe one where like D1, D2, and D3 are somehow similar. So this objective function was then fitted with experimental data in the space of pKa and pH. And this is the kind of map we obtained. So where you have the global minimum in the bottom left is the darkest area. This is where everything should be 3D particles. And the bright yellow bit is where everything should be 1D particles. And we found that if we follow the field lines of this map, we're kind of going from 1D to a 2D region to a 3D region. So this was our best estimate of what their particles would do. And when we overlaid their images with these predictions, we found pretty good agreement. So in the top right, there's a 1D zone. So most of the particles formed here are about 1D. And then everything gets a little bit wider in the 2D zone. So we get to kind of platelets. And then in the bottom part is clearly stuff that is 3D. And then also the yellow regions are kind of between 2D and 3D. And the best thing was that they had lots of other data where they couldn't extract the dimensions. And this was because everything was somehow 3D growth. And this matched really well with the predictions of where 3D growth should be. So this is just one example of how you can use a bit of AI with experiments to kind of look at morphology, and hopefully in the future we'll be doing functional properties of these particles. So I'm at the end of my talk, so let me summarize. We've developed this BOS tool based on Bayesian optimization for a very practical phase space exploration. I want to stress that we try to use this for phase space exploration with these building blocks so we can find out what are the interesting regions of phase space. And then when we found those, we can relax there instead of kind of doing relaxations more often. So this is very good for global structure search, but also for looking at properties and building up structure and property models. It does work with fewer data points than genetic algorithms and other methods like method dynamics, and it can be used to guide experiment as demonstrated by the Lookman group as well. What we use it for and what is really useful for, I recommend it for hybrid multi-component materials where you have easily defined natural chemical building blocks, stuff like supramolecular chemistry, metal organic frameworks. We're looking now increasingly into conformers and organic crystals. And we're orienting our work more towards multi-target optimization, so simultaneous energy and property optimization. These are the publications so far, and the archive that I mentioned before. And the BOS is actually a free Python tool, which is available from our GitLab for anybody who would like to try it. So we run it very frequently on big supercomputers. Thank you very much for your attention.
Thank you, Milica. Okay, so we have time for questions. If anybody has questions, please type them into the chat, or if organizers can suggest a better way to ask questions. I don't know if there's a raise hand feature on this thing or not. Maybe while people are thinking about questions, I have one, maybe two.
Sure.
If you
yeah,
do
Boris,
this,
there are quite a few audience questions I see in the
fantastic.
question.
Okay, I'll wait with my
Right.
questions then. And yeah, please go ahead. I don't know, I don't see them in the chat somehow.
Me too.
Right.
Me neither.
So in the questions box, the questions are coming in the question box. I see one from Karim. I will read your question, Karim. Can you elaborate on how to decide the building blocks? Is it done manually?
Yes, we do it manually because we usually focus on a particular system with a particular type of chemistry. And for different kinds of chemistry, we have defined different building blocks. So most frequently, we have mobile molecules near a surface where torsional angles somehow building blocks, and then the entire molecule can also like be rotated and translated. So you can like do both.
Okay, I will go next from Doyle. An intermolecular interaction is important for molecular thin film structure. How, if possible, could BOS include it? You seem like you expected this. Go ahead.
Well, this is really what we'd love to do. We want to see thin films spontaneously forming, and we would like to study the growth. So what we would like to do is organically include more molecules onto the surface. And this is unfortunately making the dimensionality of the problem very large. So we are now thinking about how to include many molecules on the surface and then define some functional forms for the energies of these monolayers, and then transform our variables from these chemically more intuitive variables to parameters that fit the functional form. And then the intermolecular interaction will be described well. So this is kind of the direction in which we're going for. So that's a good question.
Yeah, there are a lot of questions, so I will take one more and then I'll let Boris to continue perhaps. So
Everybody can write to me.
Oh, sure. Do you allow the surface to fluctuate during the simulation? This is one question from GL.
Typically not. Typically not. We are working with a lot of surfaces that are very stable. We have recently started work with some thin film surfaces, and there it's possible to use BOS and keep that thin films fixed, but afterwards there's a lot more relaxation to be done in comparison with surfaces that are more stable. So that's the answer.
Okay, so I think we can maybe give your email in chat so people can direct their questions to you. There are quite a few more.
That would be great.
Go ahead, Boris.
Mm-hmm.
I don't see the questions. Maybe my question box is missing somehow. Why don't we continue? We have 3 more minutes, I think, for Milica's questions before the next
Okay.
speaker. And then at
Great.
yeah, go ahead.
Great. So one of them is, what is the advantage of BOS compared to other automatic structure search models, such as genetic algorithm and particles form optimization from Shangang?
These two are more general, I would say. We have developed BOS specifically for these systems where we have organic and inorganic components. And there are structure search methods that are very good for molecules and structure search methods that are very good for solids. But the ones that are able to deal with both are few. And I would say these two are pretty good at that. The problem with them is that it still requires quite a lot of sampling. So we are working with colleagues who use evolutionary algorithms and genetic algorithms, and you just can't really do it without thousands of data points. So we can generally get good solutions with like hundreds or so. So that's currently the benefit for us. But I think if you can spend thousands, those other ones are probably more general and more powerful.
Thank you. And there is one from Felipe Perez. It's also on the efficiency. Would it be efficient with irregular surfaces? This is the question. Irregular surfaces may be amorphous, maybe just some irregularities. add atoms and
Yes,
defects?
yes. So we frequently work with quite corrugated surfaces. In the titanium dioxide case, the corrugation was 1.5 angstrom. That was quite big. The 6x2 copper oxide was also quite corrugated, so it had quite a lot of Z variation. So that's another reason why we like to work with this code, because you don't have to worry about that. So it's efficient.
And one more question about application. Would you see this applied to diffusion in solid? Because we mostly talked about surfaces. How would you comment on this?
Yes, we've been now thinking a lot about how to apply this to some problems in solids. You would just have to define the search variables differently. So you would have to think about, with a diffusion in solids, what are your reaction variables that are kind of critically describing the energetics of the process. If you can come up with good ones, then I think you can stick it into BOS.
Okay, can I go with one more, Boris? There is some detail about the software you use. So you use BOS, and BOS is a Python code that you just mentioned.
Yeah.
Are there any other softwares in this package that you're using? You mentioned you use.
Yes.
Go ahead.
Yes, we have to use a package for Gaussian processes. So this is really important. And we're using the GPy. We're relying on the GPy package for Gaussian processes. We've tried using also GPy opt for Bayesian optimization, but we found it had some restrictions, which we didn't want. So we kind of designed our own around GPy, the Bayesian optimization. But yeah, this is what we're building upon. So it's kind of like a big wrapper on top of GPy with more functionalities for easy use, like a binary. So it has to compile on Windows so our experimental colleagues can run it. And yeah, it's like that.
Great, thank you. Okay, one very last question. I'm sorry. This is from our past speaker. So it's from our past speaker, so I will just make an exception.
Great.
He's asking, Trevor Rohn, is there a limit to the number of atoms you can look at, or more, like what is the limit?
Nope, the limit is literally how much time you can spend computing at acquisition point. So in the past, like we've worked a lot with linear scaling DFT that really goes into hundreds and up more than 1,000 atoms. So you can really consider very large surface areas. If you're looking at defects or nanostructures that maybe require you to take its elastics in the surface into account, you need very large surface cell areas. So for that, and for big molecules as well, and self-assembly of big molecules. So we typically work with a couple of hundreds of atoms, but in principle, there is no limit to what you can do. You just need a good computer.
All right, thank you. I went through all of them as much as I could, so back to Boris.
Thank you, Emine, and thank you, Milica. Fantastic, interesting work. All right, so let's continue. So our next speaker is Albert Bartok. He is assistant professor at the University of Warwick, working jointly in the physics and engineering departments, and he's interested in developing surrogate models for electronic and atomic interactions, of course, using machine learning techniques. And he is interested in molecular crystals and liquids and condensed matter systems where large-scale simulations are needed to realistically model structure and dynamics. So, Albert.
Thank you very much for the introduction, and also thank you for making this session possible after the cancellation. It's really great to present here. So let me start this presentation by our motivation for this work. So as you can see, I have this very cartoonish graph of
Sorry, Albert. Sorry to interrupt. Sorry? I just see a blank white slide. I don't know if it's just me or everyone.
Oh.
Now I see the slide. I don't know what you did.
Oh, now I see the slide. Yes.
Okay. Is it okay now?
Yes.
Okay. I don't know, technical issues. Sorry. So this cartoon tries to represent a few typical computational techniques that people use to model materials on different scales. And on the horizontal axis, there I have this measure of coarse graining. So as you go from the left to right, you go from the smallest details of the electronic structure to on the wave function level, and then go to density functional theory, where only the electronic density is considered. You arrive at interatomic potentials, where electrons are coarse grained, and you end up with finite element where you don't even consider atoms. As you go from the left to the right, your effort also changes. So you can only do a few electrons with the full configuration interaction method, and then as you increase your level of coarse graining, you can go to bigger and larger systems for longer simulation times. So there's this hierarchy of methods. Sometimes we have the problem that as the accuracy goes down with the level of coarse graining, our simulations become less predictive. So there is this huge change between going from when we coarse grain out the electrons in terms of accuracy. So typically interatomic potentials are considered more sort of qualitative rather than predictive approaches. So my interest is to transfer this accuracy from the left to the right using machine learning, and also the motivation is that we would like accurate models, but we for example, we are not interested in electronic structure when we are interested in the big bulk of silicon, for example, and how it melts. So together with this coarse graining, we are wondering how we can make accurate models from a higher level methods. So to introduce this, I want to start from the interatomic potentials. These are these have been in the past characterized by some closed functional form, which is motivated by some physical knowledge of the system. So the simplest of these could be the Lennard-Jones model, which is based on our understanding how pair interactions work for noble gases, but it turns out also to work for some metals. Problem is that this physical understanding breaks down in different atomic arrangements. So for example, if we go from an FCC to a BCC type of metal, it cannot be represented anymore by this simple pair interaction. So we need to put in more physics. So we can, for example, do the embedded atom model, which is the second one, which will describe BCC metals very well. In other situations, we need yet other functional forms. For example, if you take a diamond configuration, you would need to introduce also directionality. So that requires yet another functional form. But again, this also breaks down when you, for example, want to study a phase transition from a diamond type configuration to beta thin. There, the fixed functional form won't work anymore. So basically, we have this limitation now that no matter how good physics we put into the functional form, as the circumstances change, our model should change as well. So this is where machine learning potentials could help. So as opposed to analytic potentials that I described in my previous slide, These utilize a much more flexible functional form, which lack physical motivation, but instead we saturate this space with data. So instead of coming up with a good theoretical formula with a few parameters, we use a lot of data obtained from mostly from electronic structure calculations. So in a bit more detail, what we are trying to achieve here is a potential energy surface fitting, where we describe our total energy as the sum of atomic contributions, and which are restricted in space. So, and some long range, which I'm going to forget about for now and just focus on these local contributions. So to put it in a bit more formal way, these environments, I show this sum as a sum of atomic energies, which depend on our neighbors within a cutoff. So that will be my model, and the physical motivation is the short-sightedness of quantum mechanics. So to put this together, we need several ingredients. One of them is a representation. So we need to somehow take our Cartesian coordinates of neighbors and make it make the machine to understand them. And the other ingredient is how to regress. So these are the regression methods. There are a number of these that are being commonly used. And finally, we need electronic structure data to fit. So I'm going to talk about each of these in a bit more detail. Before I do that, I wanted to just share my understanding how, or actually why, these machine learning potentials work at all. So let's consider this toy example here. So we start with some bug, and we want to study the vacancy formation energy. So the way it works is that we start this bug, we remove an atom, and then we let the rest of the lattice relax. So what are the ingredients here? So one of the ingredient is just the lattice energy undistorted. We can actually simulate this lattice energy by using a unit cell. This is just a very small calculation. Another ingredient was the formation of the vacancy, where we broke chemical bonds. Again, this is a fairly local event, so we can again model it using a small simulation cell. And finally, there was the relaxation of all the other atoms, which was the problem where we needed a big simulation cell. Otherwise, we would get finite size effects. So if we just do it brute force using DFT, the problem is we need to have a very large simulation box and lots of similar environments. Whereas we just broke it down into components of the problem, which can then be unified and build an atomic level model using machine learning or some other method that captures all of these ingredients in one place, and then can simulate the problem. So this is why I think these work, because you can, to study the your material, you only need relatively limited examples to train your model. So further to our ingredients, We have been using Gaussian process regression, which was already introduced by Milica, so I won't bore you with the details. The only thing I wanted to point out is how we can manipulate the covariance or kernel functions in the Gaussian model. So it's to find out what is the covariance of 2 points. We can start from the basis functions, which we integrate out using the normal distribution of the weights, and we arrive at this capital C covariance function, which doesn't have to know about the basis functions at all, and it just needs to obey a few simple things like it has to be positive definite. So given this covariance function, we then plug it into the Bayes theorem, and what we are exploiting is that we can figure out the probability distribution of a functional observation given the data. And as Milica already showed, we arrive at the closed form approximation for the mean. So again, showing a very similar graph. You have a prior, which is a set of functions, and we add the data with noise, and what we get is a prediction with error estimates that basically selects the most likely function given the data. So how are we going to use this to predict the potential energy surfaces? So as I showed before, our model is a sum of local contributions. Unfortunately, these local contributions cannot be normally measured using electronic structured data, but there is some things that can be obtained from QM calculations, and these are, for example, total energies. And that's why I showed in a bit more detail how the covariances are obtained, because we can use this knowledge to figure out what is the covariance between two total energy observations. And if you work your way through the maths on the bottom, you'll find out that these are just simply sums of covariances. So this is really just a linear operator that we can easily plug into our formulas. We can do much more than just covariances between total energies. We can compute covariances between derivative and energy observations, and also covariances between force observations. And these all are all simple derivatives of the original kernel function. So this is just basically a great framework to do fitting. So now we know how we are going to regress our data. We just another question is what is our representation? So the basic problem is that we have a set of Cartesian coordinates. We can make them relative to the central atom, and we need to come up with a vector that represents this neighborhood configuration. This runs on under different names in the community. This could be called descriptor, fingerprint, feature vector, symmetry function. It all means really the same. It's a mapping between the environment to a set of vectors. So it needs to obey some basic constraints. So, for example, as our total energy is invariant to symmetries, we expect that our representation will also be invariant to rotations, refractions, translations, and permutations. We also like our representation to be faithful, and by this I mean that we don't want two genuinely different configurations to give rise to the same representation, and I will talk about this a bit later. And finally, because our potential energy surfaces are nice smooth functions, we want this representation to also be continuous, differentiable, and smooth. So this out of the way, I just want to show what we came up eventually as a convenient representation. It's called the smooth overlap of atomic positions, where we use a set of Gaussians to represent our atomic neighborhood. So you can see a kind of a 2D projection of this. So each the central atom is in the middle, and all the neighbors are Gaussians around it. And then we also employ kind of a smooth cutoff function to make sure that as neighbors come in and out of the environment, they do it in a smooth fashion. So from this, the similarity between two neighborhoods becomes just a simple integral of these densities, which is almost good because it obeys the translational and permutational invariances. And unfortunately, if you rotate one of the environments, it will change. So we have to make it rotationally invariant, which we do by considering all possible rotations and integrating over them. And working through the algebra, it turns out that this can be constructed as a dot product of two vectors which depend on the local environment. So I won't bore you with the details. The only thing we were not able to establish back then when we developed this, whether it's a faithful representation. We ran sort of these kind of tests to see if it is, which is just, I'm showing one example here. On the left there is a reference configuration, and on the right was a kind of an initial configuration, a randomized version of this. And the question is whether if we match up the two descriptions, whether they would give rise to the same atomic configuration. And yes, indeed it does, which made us quite happy with our representation. Unfortunately, later we figured out that it's not quite the case. Our representation is not as faithful as we thought it is. And to understand what's happening here, I want to show you what are the actual terms in SOAP. So these are basically Lejeune. It's basically a histogram of trimers in the system of triangles, and in fact this is formally equivalent to a whole family of other descriptors which are listed here. And understanding this led us to realize that actually it's not difficult to construct counterexamples where we can come up with the genuinely different structures which lead to the same descriptors. So there are just two examples here shown which are genuinely different, but their angle histogram is the same. Therefore, they would have the same SOAP representation. But the same is also true for all the other descriptors in the community that use a similar setup for characterizing these triangles. Well, this is a technical problem, but it didn't stop us to come up with some great applications. So, for example, our work on silicon used this combination that I just showed you, Gaussian process regression with a SOAP representation, and this is an application on silicon. So I just want to work through these figures here. So first of all, on this, I'm not sure if okay, can you see my mouse pointer at all?
Yes.
Anyway, okay. The problem is that I cannot see it, which is so I don't really see what I'm pointing at. Okay, anyway, so I go through them from the top left corner first. So this is comparison between a number of interatomic potentials for silicon, all benchmarked against the density functional theory. Red is our model gap, and then all the others are shown in different colors. So this figure is split into two parts. On the left, there are tests which are sort of which we expect to get them right from the training data we used for fitting the potential. And on the right, we are trying to explore how transferable and how well it can extrapolate into sort of unknown configurations. So as we expected, we get these properties like elastic properties, surfaces, defect energies quite well. But we also found that, that the potential doesn't do anything particularly bad for things that are not explicitly included, like stacking faults energies. So this is a good sign, but then the potential can do a lot more. So then the next figure is a phase diagram prediction for silicon, where gray lines show experiments, and then black dots are DFT results explicitly. So this is what we are trying to reproduce rather than experiment, because DFT is our benchmark. So the red lines are our simulations, and indeed they match up quite well with DFT, and it can be regarded as a DFT quality phase diagram for silicon. And then going further and in a bit more detail, the next plot is a radial distribution function for liquid silicon, and then again DFT and gap match quite well, and you can see that some of the more traditional interatomic potentials give some quite unrealistic RDFs. And below that is the same for angles. That's the angle distribution function, and again gap reproduces the DFT results quite well. So there are some more interesting tests, and I'm going to just go now from the bottom, from the right to the left now. So this figure would be a path between the fourfold defect reconstruction into pure bulk, and you can see that even though the gap line doesn't match the DFT line perfectly, in fact, we are missing the barrier. What you can see here coded by the colors are the predicted errors that are coming from the Gaussian process error prediction. The method can actually quantify to a degree the error it makes on the prediction, and it shows that in red that those are predictions where it's quite uncertain, and as it gets close to the bulk, the predictions are getting much smaller. So it's another nice feature that even though the method is not perfect, mostly because these configurations were not trained on, it makes prediction. It can also quantify the uncertainty. Further to the left, there is a crack tip simulation, again color-coded by predicted errors. The good thing is that this is a realistic crack, so it's basically the same that some of us found in DFT quite a few years before. So the surface reconstruction and the way the crack tip propagates is completely realistic. And finally, and this is perhaps the most important test of all, is a random structure search on silicon, where we basically started geometry optimizations from completely random arrangement of atoms, and then relaxed these using different potential energy surfaces. So different colors are different models. Black is DFT, red is gap, and all the rest are different interatomic potentials. And you can see that they scatter quite a bit, and only gap is the one where the envelope of energies and volumes, this kind of convex hull, match quite closely, and all the other methods find widely unrealistic configurations. And finally, before I wrap up, I just wanted to show another application of the SOAP method, where we explored how well can SOAP quantify atomic similarity. So perhaps the most interesting figure is in the bottom right, where we trained a model to compare different enzyme activity in for the different binding of ligands to an enzyme, just based on a data set of whether a ligand binds to an enzyme or not, and we achieved not only a great accuracy, but also the method was able to highlight the bits of the molecule shown in red, which is binding to the enzyme pocket, discovered purely based on the similarities. And with this, I would like to conclude my talk. What we are doing here is we are informing models based on higher level theory. So in our case, potential energy surfaces from electronic structure data, and the machine learning glues it all together. And thank you for your attention.
Thank you, Albert, very much. So now we have time for questions. You can raise your hand, or you can type your question in the question box. Okay. So we have one question from Huta Banjade. I'm going to unmute Huta and in a second. Okay, go ahead with your question. Huta, do you want to ask your question? Okay, I'll read the question. How do you consider neighbors on a site in the crystal as the radius vary, and it's difficult to have a single cutoff for neighbors in all crystals?
Well, the cutoff is a very physical thing. So it depends on the material that we are studying, and then it's well, given the force constant matrix of the material of interest, it's we can quantify what is the cutoff that we are happy with. So given the cutoff, there will be an error associated with the prediction, which will be inherent because the model won't know anything beyond that cutoff, and then we just decide on what is our trade-off between computational efficiency and accuracy based on this.
Thank you. So the next question is from Mohammed Shwaibi. Mohammed, I unmuted you, so you can try to ask your question if this works.
Hello, can you hear me?
Yes.
Yes.
Okay, thanks for the great talk. I just had a quick question. I mean, there's a variety of models out there and methods to do these kind of machine learning potentials. In your experience, what are the drawbacks and some of the limitations that come with GAP and other kernel-based methods to that of, say, neural networks, for example?
So I didn't talk about a lot of details, but for example, in neural networks, I think a great advantage would be that once you fix your neural network architecture, your prediction cost will be fixed. With GAP, it's slightly different because as it's a Gaussian process-based method. As you increase your database, for example, you would expect that your prediction cost also goes up. So basically, if you think of the Gaussian process as based on basis functions, you would be using more basis functions as your input data gets larger. We get around this to a degree by using sparsification, which I didn't mention at all in this talk, but obviously it has limitations. But you kind of hit the same wall when you are using a neural network in the end, because you need a complex enough neural network to accurately or more flexibly enough which is flexible enough to model your data. So I think this would be perhaps the most obvious difference between a neural network and the Gaussian process.
And
the advantage is that you get these variance estimates in a quite straightforward way from a Gaussian process.
All right, thank you.
Okay, the next question is from Jean-Luc Fatbert. I'm going to unmute. Go ahead.
Hi, my question is about energy conservation. How good is it in this ML potential? It's
perfect. It's because the forces are analytic derivatives of the energy. The energy conservation is perfect. The only perfect in theory, in practice, it's as compared to, say, traditional interatomic potential, you have a lot more terms, so you introduce a bit more numerical errors when you evaluate your energies and the gradients. But I've never seen it being a problem, not even in a microcanonical simulation.
Okay, thank you.
Okay, I think we're through all the questions. So Albert, thank you very much for the fantastic talk.
Well, thank you very much for inviting me.
Okay, so moving right along and continuing the theme with Gaussian process methods. The next speaker is Jonathan Vandermause. He received his bachelor's degrees in math and physics from Dartmouth College and is currently a graduate student in the physics department at Harvard. And he's interested in condensed matter theory, Bayesian machine learning methods, and their intersection. So, John, the floor is yours. I think you're muted somehow. Wait a second.
Can you hear me now?
Yes, now we can hear you.
Okay, great. So thank you, Boris, for the introduction, and thank you everyone for tuning in to the webinar. I'm going to talk a little bit about how you can sort of use the uncertainties that come out of Gaussian process models to automate the process of training a machine learned potential. So the method that we've been using is called FLARE, which stands for Fast Learning of Atomistic Rare Events. And really, at the heart of the method is Gaussian process regression. So we're constructing force fields with a GP so that we can get not just estimates of force components on atoms, but also error bars on those force components. With the ultimate goal being, creating force fields that are applicable for multi-element systems, and that can be scaled up to fairly large systems. So this diagram here sort of gives you an overview of how the method works. So essentially, you start with nothing in your training set, and you make a call to density functional theory on some sort of DFT-sized simulation cell that represents what you want to simulate. And you use those DFT forces to train an initial model, an initial force field. And because the GP is Bayesian, you can sort of check how it's doing at each step in your molecular dynamics simulation. So if you judge that the errors on your force components are unacceptably high, you sort of stay in this right loop here, where you evaluate forces with DFT, and typically that's quite expensive. And then you update the model to sort of improve the training set and get improved estimates of forces in your system. So you sort of keep doing this until eventually your errors drop below some chosen threshold, at which point you can let the Gaussian process model take over. And typically it's several orders of magnitude faster than evaluating forces with DFT. And so now the GP is updating the positions and predicting the forces. And if at some point in your simulation you sort of hit something new, you encounter some sort of novel region of phase space, or you turn up the temperature or something, and your errors are calibrated properly, your model should be able to tell you that you need additional reference data. Okay, so if that ever happens in the course of this simulation, you sort of return to the right loop, you make additional calls to DFT to get your model in good shape, and then you continue on the sort of on the highway here on the left. So that's the training procedure that we are working with. And once that's done, you can take the GP, and we've implemented it in the software LAMPS, which allows us to tackle fairly large systems over reasonably long timescales. So I'll talk about this specific example of silver iodide, which is a fast ion conductor, toward the end of the talk. But the main point is we're sort of able to scale this up to tens of thousands of atoms, nanosecond or even microsecond timescales fairly comfortably once we're done training the GP. So that's an overview of the method. And I'll just mention that this sort of idea of trying to learn a force field automatically or to even do it on the fly during a molecular dynamics simulation is becoming increasingly popular. So one of the first approaches was proposed back in 2015, also using a GP, but sort of used the exact error of the Gaussian process. So you had to evaluate the DFT forces at every time step in order to tell if your forces are good or not. And then there have been a range of different proposals over the years. Alexander Shapiv uses linear regression using his moment tensor framework, which doesn't exploit Bayesian uncertainties, but sort of has some other measure called the d-optimality criterion of distance from the training set. Within the Gaussian approximation framework, sort of automated random structure search protocols are becoming popular, where you can sort of start with a random structure and iteratively kind of relax the structures with your model and converge your way toward a good model of the potential energy surface. More recently, and very much in line with what I'll be talking about, is recent work by Janucci and the folks behind the VASP software. They use Bayesian linear regression and essentially a multi-element version of the SOAP kernel to sort of implement this on-the-fly learning protocol. So what I'll be talking about today is sort of our approach to this. We simplify the kernel by focusing explicitly on 2- and 3-body interactions. So at the end of the day, the force field that we learn is quite low dimensional, and it can be mapped to much faster regression models like cubic splines is what we use in practice. And for us, the convenient thing about this approach is it allows you to tackle fairly large systems and to study molecular dynamic simulations that can go up to microsecond timescales. So that's sort of a broad picture of where the field is right now, and it's constantly developing, and it's definitely an active area. So Albert gave some really good introduction to this general idea, and I'll just touch on a few points that are specific to our kind of spin on modeling the potential energy surface. So quite generally, what we're trying to do is build a model of the Born-Oppenheimer, potential energy surface, which is this kind of high-dimensional object. In full generality, it takes as input the coordinates of all of the atoms in the system. So if you have a really large collection of atoms, of n atoms, this is going to be a function of 3 times n coordinates, and it's this sort of high-dimensional beast. So what we do in practice, and this goes along with what Albert described in the last presentation, is we make this assumption of locality. So you take your collection of atoms, and for atom, let's say I in the material, you sort of restrict your focus to just a local environment, a spherical local environment that is surrounding that atom. And you assume that the atom I can be assigned a local energy. Okay, and we sort of go a step further and we say that the local energy can be expressed as a sum over even lower dimensional contributions. So we assume that pairs of atoms and triplets of atoms make contributions to the total energy, the total local energy of this atom. And that has the effect of simplifying the regression task quite a bit. So now instead of having to learn this fully general potential energy surface, which is high dimensional, the task is to learn these 2- and 3-body contributions to the energy. So basically, for every pair of atoms that falls inside of the 2-body cutoff sphere, there's this 2-body contribution that depends on the species of the atoms. And for every triplet inside of the 3-body sphere, there's this 3-body contribution. Okay, and to make this sort of multi-element and generalizable to pretty much any type of system that you like, we make this assumption that there's species dependence. So different pairs of species in the 2-body case have a totally different pair energy function associated with it. But we don't make any assumption about what the analytic form of these 2- and 3-body contributions are. They're sort of non-parametric, and we let the Gaussian process deduce what the best function is that can match the ab initio data in the best way. So this is the kind of idea behind the low-dimensional force fields that we like to use in practice. And now I'll say a few words about the actual kernel that we use in the Gaussian process regression model. So whenever you train a GP, you have to select a kernel, as Albert mentioned in the last talk. I'll just focus on the two-body case. The three-body case is quite similar, but instead of dealing with pairs of atoms, you have to sort of compare triplets, but the idea is essentially the same. So what we do, our features essentially are interatomic distances. We work directly with just the distance between two atoms, and we pass the difference between the distance through this squared exponential kernel. We also include a smooth cutoff function, which is quite typical. This sort of ensures that the potential energy surface isn't going to sharply change as you put atoms in and out of the cutoff sphere. And we also want this to be a multi-element approach. And so the idea here is to introduce these Kronecker deltas. Okay, this introduces the species dependence of the kernel. So if the species of the two pairs that you're comparing don't match up, then the Kronecker deltas here will evaluate to 0. And essentially, that's saying that these two objects that we're comparing are infinitely distant from each other. And the effect that has, on the regression model is we're totally separating the model associated with different pairs. Okay, so distinct pairs get distinct functions that get learned through the training process. So this is the sort of pair energy kernel that we use. And then in order to sort of train directly on forces, we take derivatives of this kernel with respect to the Cartesian coordinates of the atoms, which gives you sort of a totally rotationally covariant model of forces in the end. And you'll notice there are sort of a few free parameters in this expression for the kernel. And I'll say a few words about what those mean. They sort of have direct interpretations. So the L term here showing up in the squared exponential kernel is the length scale of the GP. And ultimately, it's going to determine sort of how wiggly your potential energy surface is going to be in the end. So the smaller the value of L is, sort of the more rapidly it's going to vary in space. The sigma parameter that's out front here, it's sometimes called the signal variance in the Gaussian process literature. That's going to determine essentially the size of your error bars. So if you take your test point, really far away from your training manifold, and you ask what is the uncertainty on that point, that's going to be determined by the value of the signal variance. And finally, there's a noise uncertainty that shows up in the covariance matrix of the GP, which is associated with fundamental variation in the data that your model isn't able to capture for various reasons. And so what you want to do in order to sort of get the best possible model performance is to rigorously optimize these hyperparameters. And within the GP framework, there's sort of a tractable way of doing that. You can explicitly evaluate this marginal likelihood function and try to search for the parameters that maximize the log marginal likelihood, which can give you sort of very important effects on the quality of your errors and also the performance of the model. So that's essentially the kernel that we use, and we feed that into the Gaussian process. And I'll go kind of quickly over the sort of GP formalism, because I think it's been touched upon quite a bit in the past talks. So on the right here is sort of the classic picture of a one-dimensional Gaussian process. So the x's here are the training points in this case. And you can see when you're right on top of a training point, the uncertainties are quite low. Okay, so they go to 0 if your function is noiseless. And as you move away from the training points, you can see the error bars increase. Okay, and so this is the nice property of GPs. You sort of have this way of gauging how far away you are from the training data. Okay, so if you move away from what the GP has been trained on, the error bars tend to increase if they're calibrated properly. And the way that forces get predicted with the GP is essentially by performing a weighted sum over kernels between the test point call it the atomic environment I, and all of the training atomic environments in your training set, rho T. Okay, and this alpha vector basically comes out of the linear algebra of the GP fit. And so that's how we estimate the mean of the predictive posterior distribution. And the really convenient thing about GPs that sort of sets it apart from other regression models like neural networks is that you can get sort of an explicit analytic expression for the variance of the predictive posterior. So I've written out the formula here. The key thing I want to sort of draw your attention to is that the variance breaks down into two different contributions. There's one contribution that I'll call the epistemic uncertainty. This is characterizing essentially how far away you are from the training data. And then there's this noise parameter that gets optimized by maximizing the log marginal likelihood. And it tells you, basically how well is your model doing overall, what is like the baseline error level of the model. And these two pieces of the uncertainty can give you really rich information about how the model is doing at a particular test point. And so I'd like to sort of drill down a little bit more and say a bit more about what these uncertainties mean in the context of atomistic simulation. So to show you one simple example of fitting an aluminum force field, here on the x-axis, I'm sweeping the cutoff radius of the atomic environment. So this is controlling the degree of locality of the model. And as we sort of increase the cutoff, we're including more and more atoms inside of the cutoff sphere. And the dotted line here is sort of the true error. So it's the difference between our ab initio values and the predictions of the model. And you can see, this is sort of the typical picture that you see. As you increase the cutoff, the error goes down up to a certain point, and you eventually sort of converge the error. So at a certain point, expanding the radius doesn't really allow you to improve the error very much. But the thing to notice is that our noise parameter, which we're optimizing for each of these models, it sort of gives you an indicator of how well the model is doing. It's this kind of internal measure of model error, and it tracks the true error in this nice way. So it's giving you a measure of essentially for a given cutoff radius, how well can you expect to do without having to evaluate errors on an independent test set. So that's the noise uncertainty. The epistemic uncertainty is telling you what happens as I take atomic configurations that look really different from what the model has been trained on. So to give you sort of an example, here we trained a model on sort of a barely perturbed aluminum structure. And then we asked the Gaussian process, what is the error as we sort of increase the size of our random perturbations of this structure, okay? And again, the dotted line is the true error. And as we increase the perturbation size, the size of the error increases. The solid line here is this epistemic uncertainty averaged over all of the force components in the simulation cell. And you can see basically the behavior that you expect. As you sort of take the structure away from the training set, the epistemic uncertainty increases, and it saturates a certain bound that's tied to the signal variance of the model. Okay, so you sort of hit this point where the uncertainty is as big as it could possibly be given the hyperparameters that you currently have, which sort of emphasizes the importance of making sure that you sort of update the hyperparameters as more data comes online. So these are the two uncertainties that sort of contribute to the total uncertainty estimate of the Gaussian process. And we can use these two different uncertainties, the noise uncertainty and the epistemic uncertainty, to define a decision criterion about when we need more data. The idea here is that, if the epistemic uncertainty starts to dominate, if it goes way above the noise of the model, that's a signal that more data is needed, that you're sort of evaluating the GP on a new structure that isn't going to give very good results. Okay, so whenever the epistemic uncertainty goes above the noise, we sort of make a call to DFT, and we update the training set of the model. So that's kind of the general framework, theoretical framework. And in the second half of the talk, I'll go through a few examples of different systems that we've applied this approach to, starting with a kind of toy example. So here we have a 32 atom supercell of aluminum, and we're initializing the system at a fairly low temperature in the FCC phase. Okay, so around 100 to 200 Kelvin. And again, we're starting with nothing in the training set. So initially the GP knows nothing about the potential energy surface. And every black dot that you see here is a call that's made to DFT during this on-the-fly molecular dynamics simulation. So at the very beginning, we need a bunch of DFT calls. You can see the cluster of black dots here. And then as the simulation proceeds, we need fewer and fewer as the model gains confidence about what's going on with the forces in FCC aluminum. And then the test to see if we could be sensitive to new environments was to essentially increase the temperature to a very large value to melt the crystal halfway through the simulation. So you can see it at 5 picoseconds here, we sort of rescale the velocities all the way up to 5,000 Kelvin, which is way above the melting point of aluminum. And we check to see if the uncertainties are unacceptably high. And you can see another cluster of DFT calls are made immediately after we melt the crystal. Okay, so the model is sort of sensitive to the fact that we've entered a new phase of matter, that now we're dealing with molten aluminum rather than just simple FCC aluminum. But then as the simulation proceeds, again, we need fewer and fewer calls to DFT. And here, just to give you kind of a visual, this is the full on-the-fly simulation. So we start in the FCC phase, and then we melt the crystal. And we essentially just wanted to show we're able to detect new phases, and we can sort of iteratively improve the model in a single molecular dynamics simulation. And just to sort of benchmark how well we're doing relative to a few other aluminum potentials, here we're comparing against an EAM potential, which is one of the faster classical force fields out there, but doesn't necessarily give the best accuracy. And we compare it against another sort of off-the-shelf neural network model. And you can see the errors look quite good. And equally important for us is that we were able to get a very efficient model after mapping the Gaussian process to cubic splines. Okay, so because we're sort of making this assumption that the potential energy surface breaks into these 2 and 3 body terms, we can map those low dimensional terms directly, implemented in lamps, and get potentials that are quite competitive. So you can see our 2-body model shown in green here is roughly the same order of magnitude as the EAM potential. 2 plus 3 is about an order of magnitude slower than 2-body, but still in quite a reasonable range where you can sort of handle fairly long simulations and big system sizes. Okay, so that's aluminum, and we can just like slowly dial up the complexity of these systems. So here I'm basically just taking that aluminum supercell and removing 1 atom to create a vacancy. And we wanted to see, are we able to properly model vacancy diffusion? So again, we start with an empty training set, and we have a bunch of DFT calls initially as the model uncertainty is quite high. And after that initial period of DFT calls, the model takes over. And what I'm plotting here is the mean squared displacement of the system as a function of time. So every time the vacancy makes a hop, you see a sharp increase in the MSD or decrease in the MSD. And so basically the model is correctly modeling how the vacancy moves around. So every few hundred picoseconds or so, the vacancy makes this sharp hop. And you can see that happen over a nanosecond timescale. That's how long we ran this particular training simulation. And to check the energetics, we can compare against our ground truth, which for us is DFT. And so here we're looking at what is the energy barrier of vacancy migration. The blue line is the prediction of the GP, dotted is DFT, and you can see there's very good overlap. So we can kind of trust the dynamics that are predicted by the model. Okay, so a slightly more complex system going beyond aluminum. This is the system I alluded to at the beginning of the talk. It's the fast ion conductor silver iodide, which exhibits kind of interesting structural and dynamic properties. So above 420 Kelvin, this system basically enters into a superionic phase where the silvers in the material start diffusing almost like a liquid, while the iodines are sort of rigidly located at their lattice sites. And we wanted to see if we could correctly model the fast ion behavior of this material. So we went through this three-stage training process where we cranked up the temperature in an on-the-fly simulation at 2 different stages. And you can see the black dots again are every point at which we made a call to DFT. And then we took that final model and we ran sort of big simulations of about 10,000 atoms at various temperatures. And you can see here that we're sort of correctly modeling the 2 different phases that appear, that are sort of experimentally known to appear in this material. Above 420 Kelvin, we get this nice cubic BCC phase with the silvers sort of zipping through the material. Below 420 Kelvin, we have this hexagonal close packed phase where nothing terribly interesting is happening. The silvers are kind of locked down in the crystal. And so the ultimate test is how well do the diffusivities of the silver compare to both AIMD and experimental values. So this system has been studied for several decades, and there's quite a bit of experimental data out there to compare to. And you can see we're getting the activation energy of diffusion pretty much correct. So there's good overlap with AIMD, which is sort of our ground truth. How are we comparing to density functional theory? But also, for this material, DFT doesn't do a terrible job. There's reasonable agreement with experiment. So that's an encouraging sign that we can start to sort of apply this to more complex materials. And we've looked at a few different systems. So 2-dimensional boron nitride, the shape memory alloy nickel titanium, simple materials like carbon and silicon. But to conclude the talk, I wanted to go over a recent application to a system in catalysis. So this is a bimetallic system consisting of silver atoms and a palladium island on top. This is work that was done in collaboration with David Lim at Harvard. So here what we're doing is taking an AIMD training simulation and then performing active learning on it. So we go frame by frame through the simulation and we select the environments that give the highest uncertainties in the GP. Okay, so in the end, for this system, actually, it's a surprisingly modest amount of data that we need to converge the model. And then we can take it, compare it to off-the-shelf force fields. So you can see here, EAM doesn't do the best job of modeling surfaces for this material, whereas we're sort of training directly on ab initio data, and so we get pretty good agreement with DFT. And what we did with the final model was we applied it to microsecond timescales to see what are the restructuring mechanisms of this palladium island as a function of time. And you can see sort of non-trivial kind of interesting behavior happening here where silver atoms climb on top of the island slowly over time. And that introduces these vacancies in the silver surface that sort of grow over time and form vacancy pits. And those vacancy pits move around and they combine with each other. And it's this kind of non-trivial phenomenology that's emerging at the microsecond timescale. And we can compare it to experiments. So this is STM images coming out of Cynthia Friend's group at Harvard. Essentially the same system where palladium was deposited on top of silver, and they looked at what happened when you anneal it at various temperatures. And they saw essentially the same type of behavior where vacancy, these sort of large-scale vacancy pits start to form on the first layer of the material. So with that, I'd like to thank you for your attention and point you to the paper that was recently published last month, as well as our code. It's totally open source and documented, so if you're interested, please do check that out. And I'd like to thank all of the people at Harvard who have contributed to this project over the last year. And with that, I'd like to thank you for your attention, and I'd be happy to take any questions.
Great, thank you, John. All right, so we have time for a couple of questions. Okay, so we have one question from Leonid Kale. Leonid, I'm gonna unmute you in a second. Go ahead. Leonid, can you ask your question, or should I read it? Okay, I'm gonna read Leonid's question. Okay, so how do you deal with the fact that you have no constant of motion?
No constant of motion. So in these training simulations that I showed, we do have a conserved quantity, which is energy. So so for example, here we're essentially working in the NVE ensemble, so energy is conserved. And so the temperature fluctuates because we're not controlling temperature explicitly, but it sort of fluctuates within a reasonable range of values. So yeah, because we're sort of careful about making sure that forces come from a gradient of a global energy, we're always able to conserve energy with these simulations. So it's not really an issue in practice.
I guess I can also interpret this question as saying that your potential model changes with time as you do the training. That question gets also asked quite a bit. I don't know if that's what Leonid meant.
Yeah, so that's a good point, and that's definitely true. So yeah, while you're training, the energy model is constantly changing. So as a new DFT calculation is introduced, yeah, you have a different model. But the point is, it's only changing during this training phase. And once you're happy with the final model, you sort of fix it. And at that point, the energetics are totally fixed and nothing is changing. So in practice, it doesn't seem to be much of an issue.
All right, so the next question comes from Mohammed Shwaibi. I'm going to unmute Mohammed, see if he can ask the question himself.
Hello, can you hear me?
Yes.
All right, thanks, Jonathan. That was a great talk. I had a question more from the practical side. So when you talked about the uncertainty thresholds, was that like an empirical decision you guys made? Did you guys like play around with a variety of thresholds, or was there something more systematic? And still on that note of uncertainty, you talked about how you get these uncertainties on a per atom basis. Were you looking at defining the uncertainty as being the max uncertainty across all atoms, or where were your experience?
Yeah, good questions. So regarding the threshold, so that is a free parameter, and you can decide, how much uncertainty is too much uncertainty. What works for us in practice is to tie the threshold to the value of the noise parameter. So basically, in many of these applications, we say, if the force component on any atom has an epistemic uncertainty that exceeds the value of the noise parameter, that's a sign that we need to make a DFT calculation and update the model. And then, there's some wiggle room there. You can say, all right, maybe I'm comfortable with the epistemic uncertainty being within, 2 times the noise parameter or whatever. And the choice that you make is going to have an effect on how many DFT calls get made during the simulation. But it's definitely a sort of free parameter that can be played around with. And for different systems, it might make sense to choose different values. Regarding per atom uncertainties, right, so every force component has an uncertainty associated with it. So in this plot, for example, I'm just averaging over all of those uncertainties in the full structure. But when we make a judgment about sort of making a call to DFT, we basically look at each force component and check if it's above the threshold or below. And if any force component is above, we make a call to DFT.
Thank you.
Okay, next question is from Aidan Thompson. Let me unmute Aidan.
Hi, can you hear me okay?
Yep.
Yes.
So my question is pretty simple. I just want to know if this kind of analysis can be applied to linear regression as a special case.
Yeah, that's a good point. So linear models, like Gaussian processes, are really nice in that they can give you sort of explicit expressions for the variance. And there are a bunch of linear models out there. So of course, SNAP and QSNAP are two examples of that. Also, the moment tensor potential framework is linear. So yeah, but basically this kind of idea could be applied to those models. Basically, you would need to be careful about sort of writing down a Bayesian linear regression model and making sure that the hyperparameters of that model are sort of properly tuned. But it should give you sort of reliable uncertainties, and I don't see any reason why you couldn't sort of apply the same kind of on the fly framework to those kind of linear approaches. So yeah, I think it should work.
Great. So one question from Mohammed Abdelghani. Mohammed, go ahead. Okay, maybe I'll read the question. Are there limitations on the system size that you expect for these techniques if applied on systems like multi-component alloys, like high entropy alloys?
Right. So the size constraint that's most painful, I would say, for us is basically the fact that we're limited in the training phase to systems that we can evaluate with DFT. So, you know, in these examples, we're not going past, 100 atoms or so, just because it becomes expensive to evaluate the forces with DFT. But once the training's done, you essentially have a force field that's roughly as fast as like Stillinger-Weber type force fields, maybe a little bit slower. So at that point, you really can scale it up pretty much as big as you can scale up classical force fields. I think the big challenge is being able to apply this sort of active learning workflow to bigger training systems to try to sort of evaluate which part of a big structure you're uncertain about, and then finding a smart way of kind of carving out that part of the system and evaluating the forces on those atoms with DFT. I think in principle, an approach like that could work. You just have to be very careful about how exactly you sort of carve out the system of interest. But yeah, that's definitely like the limiting factor of this kind of approach.
Great. So we have one hand raised from Chanbum Park, and I'm unable to unmute Chanbum. So I don't know what the question is. So Chanbum, if you want to unmute yourself and ask the question, go ahead. Or otherwise, I think we have. Go ahead. I just saw your microphone unmute. Yes.
Yeah. Can you apply your model to polymers? And how do you deal with the long range force?
Yeah, good question. So yeah, polymers are super interesting systems, and we're starting to look at it a little bit. The important thing that shows up in polymer systems that isn't necessarily as important in the systems that I showed are four-body interactions. So dihedrals start to become important. So if you look at force fields like OPLS, those have explicit dihedral terms in them, and they're there for a reason. So it's sort of an important part of the physics of that system. So I think if you want to apply this to complex polymer systems, you have to be careful about the kernel that you choose, and it's quite possible that 2 and 3 body kernels are not going to do the job, and you need to sort of introduce, at the very least, like a 4-body contribution to the energy, probably like a full-blown many-body contribution, like the SOAP kernel would make sense. So yeah, if you want to sort of dial up complexity, you also have to have an associated increase in the complexity of the kernel. As for long-range forces, that's definitely an open issue. And I think a number of groups are thinking about it, but there hasn't been like a slam dunk solution to this problem. Basically, what you want is a model that can allow you to predict partial charges that are somehow dependent on what's happening in the atomic environment. So you should be able to have some time dependence in your assignment of partial charges. And to do that in a way that exactly conserves charge is not so easy. It's possible that there's a path forward where you train on things like electric dipole moments that you can in principle calculate with DFT, but you never actually observe the partial charges explicitly. So yeah, there are several reasons why it's a hard problem, but I think that's probably the direction that the field is going in, and maybe in the next few years we'll see a good solution to it.
Great, I think that's all the questions we had. Thank you, Jonathan. And thanks to all the speakers for the fantastic talks. I think this was a very, very interesting, important session. Hopefully one out of more to follow. So I just wanted to give the opportunity to the organizers. Gia, do you want to say anything in conclusion?
Yeah, absolutely. Thank you, Boris and Emily, for organizing such a fantastic session, and especially I want to thank Milica, Albert, and John for the great talks. For all of the meeting attendees and registrants, we will be sending out links to the recorded session on YouTube very soon, and also we will send you information regarding the next webinar. So please stay tuned with us, and thank you very much.
Okay, great. Thank you, everyone. Take care.